Okay, so welcome to Anatoly Dymarsky, who came from University of Kentucky, and he will give a talk about Eigenstate Thermalization Hypothesis from interacting qubits to QFT.
Yes, hello. Thank you very much for inviting me to give a lecture here. It is both my pleasure and an honor to give this lecture. My understanding is that I'm the first guest lecturer this semester during this course, so that gives me extra responsibility. I will try to give a lecture overviewing the Eigenstate Thermalization Hypothesis. This is a topic of my research. And I will try to make it connected logically to the lecture we just had about quantum ergodicity and quantum chaos. I realize, though, that my lecture is missing a lot of context. I was preparing this lecture without fully understanding which material will be presented at the first lecture and what will be the background. I knew that I will be speaking to mathematicians, so I was very careful writing slides. There are no words proof or definition, because I wanted to avoid any false pretense that I'm saying something rigorous. But otherwise, I probably did not provide enough context. Anyway, we have a Blackboard here, so I will try to use Blackboard if necessary. So let me start. And my first slide is actually, I sort of anticipated that the first lecture will be about quantum chaos, how it is understood in the single particle context. So let me go back to the lecture we just heard and try to sort of explain how I think about it and this topic in general. So the topic of quantum chaos historically started with the observation by Wigner, which we already heard about today. That's the observation that if you try to look at the energy levels of complex nuclei, then it's very difficult to propose a theory which will predict individual properties of those energy levels. So to predict the value of an individual energy level is very, very difficult. But nevertheless, Wigner noticed, it was an observation. I'm not trying to give a historical overview. I'm trying to explain my understanding of the subject. That he saw an observation. It was a core observation that if you start to approach this energy level statistically, then there is some predictive power. And we saw some plots from the original papers. If you try to superimpose the plots, histograms, showing the mean level spacing between energy levels of complex nuclei, then you see that they fall into a nice curve, and Wigner proposed what the curve would be. His proposal was very close to the exact one, but not the rigorous one. In the literature, this is known as Wigner surmise, and you can look at Wikipedia what literally that is. That's a solution to a very simple problem, 2x2 matrix. And then later on, people came up with a more precise formulation. I would avoid words rigorous, because first of all, it's not only about rigor. Of course, it's also about rigor, but it's also about physical message. When I say precise formulation, I mean what kind of things people focus on. So perhaps in the original observation of Wigner, he saw that you can try to predict certain statistical properties of energy levels, certain statistical properties, let's say mean level spacing. But later on, people understood, and this is known currently as the Bahigas-Ganoni-Schmidt conjecture, that all statistical properties of energy levels can be understood in terms of some underlying theory, which happens to be the random matrix theory. So this, I will try to use the pointer, this formulation, I'm not sure, can you see my pointer? Yes. So this formulation is more precise because it tells you exactly what is the universality, what are the universal properties you are looking at. Then, of course, we need to discuss physical significance. Of course, as a mathematical statement, if it is either correct or not correct, but to be interesting, it has to be some physical significance. In this case, I'm not talking about some experiment, but if you think that something is interesting, that gives it significance. What is the physical significance of energy levels? It's actually difficult to explain, because if you try to observe a practical observational difference between the system with different level statistics, you will need to set up an experiment which either invoke very late times, maybe exponential, maybe not exponential, that's a detailed conversation to have, or it should have exponential sensitivity. Naively, you need to have an experiment which is exponentially sensitive, because energy levels are exponentially close to each other. It depends on the system, and that's perhaps a mistake I'm making, because I'm always thinking about system what is called many-body systems. I'll explain what it is in a second. But in any case, physical significance is not so obvious. In other words, you can consider two systems. One would exhibit one level statistics, another will exhibit another level statistics, but doing an experiment to distinguish one from another is very difficult. Of course, mathematically, it's a stark difference, but physical significance is not obvious. Nevertheless, it's a very interesting question to understand what that physical significance is. And then finally, the derivation. I would not say the word proof. Of course, if you have some mathematical theorem, you can prove it and say, that's it, that's the end of the story. But for me, it's more important to understand what is behind this kind of behavior. So the word derivation better explains that, because I want to understand the roots of this behavior. So in case of the level statistics, that wasn't discussed in the lecture today, but perhaps will be discussed later in the course. With the level statistics, at least in the semi-classical setting, people do understand where level statistics comes from. It comes from certain behavior of classical trajectories, which falls into the category of being chaotic. The trajectories fall from each other exponentially. So this is sort of a template. This topic of quantum chaos is rather well developed. There are even some rigorous results, as we learned today. But I want to present Eigenstate Thermalization Hypothesis according to this template. And before I start doing that, maybe I should make a disclaimer. So I did not realize that preparing for my lecture, but most of the examples we saw in the lecture today, they are concerned with what is called one-particle systems. So you have a system, physical system, which describes one particle which moves somewhere. It could be a graph, it could be a manifold, a Sinai billiard, it could be a Riemann surface. I even saw recently a numerical paper discussing a particle moving a complex Calabi-Yau, where they also saw random matrix theory statistics. All of these systems, they have something in common. There's a single particle systems. The density of states, density of levels, grows polynomially with volume or with energy. So these systems are more tractable than what is called many-body systems. Many-body systems, when you put a lot of particles in the same volume and they interact, and you can have systems with classical limit, that's when you have classical particles, or you can have systems without classical limit when you have interacting spins. And the difference of many-body physics is that it's more complex because you have exponential density of states. If you change energy by a finite amount, by 10%, the number of states with that energy grows exponentially. So that makes things much more complicated. And the standard example I will be thinking about today is a many-body example, which is the best example to think about is the spin chain. So I wrote some model Hamiltonian. That's the simplest Hamiltonian you can write in one dimensions, called the Eisen model, non-integrable Eisen model. It describes L spins, and then it will be 2 to the L possible states, where spin is an arrow which goes up and down, or 0 and 1. We have exactly 2 to the L strings of length L, consisting of 0 and 1s. So these are all possible quantum states of your system. That's rather different with the first quantized or single particle story, when you have L sites, and particle could be at only one of those L sites, or of course a superposition. So in the first quantized story, in the single particle story, you have a graph of L sites, the Hilbert space size L. Second quantized story, many body story, you have a graph of L sites, you have 2 to the L or exponent to the L many states. You see the difference. So I will be mostly talking about this scenario, but of course, I don't want to say that ETH is restricted to this scenario. Somehow, currently in physics, because these things are more complicated, ETH is studied in this context, but I want to emphasize in my talk that there are many interesting open questions which should be understood first in the single quantized context. Okay. All right, so let's start with the ETH. I will try to follow, in my talk, I will try to follow the same template. I will say the word ETH maybe 50,000 times. So first, I'll explain what it is. Eigenstate Thermalization Hypothesis. Since this moment on, I will simply say ETH, but I will try to explain what it is. First, the core observation. So first, I'll try to convince you that there is some reasonable phenomenon to discuss, that there is some interesting core, that there is some interesting behavior which is obvious and worth studying. So this is first an observation. Then precise formulation. I will speak about formulation, which I think is more precise than a naive one, but I put the question mark because we really don't know what the precise formulation is. And let me remind you, precise formulation, it's not only about the rigor, but also about universality. You want to formulate properties which you truly care about. So as time goes on, it might be that aspects we really need to be thinking about are slightly different from the aspects we first encountered. So in the Wigner case, in the level statistic case, there was a difference between Bahiga's conjecture and Wigner summarize. So I want to emphasize that here as well, the original formulation of ETH in the end of the story could be rather different from what we understand as ETH 20 years from now. We will speak a little bit about physical significance. It has the name of quantum ergodicity, but it's slightly different quantum ergodicity from the one we have in the talk before, and I will explain the difference. And then we will speak about the derivation, but there are also question marks here because we really don't know how to prove anything when it comes to non-integrable many-body systems. Even we can go one step back and speak about quantum chaos. We can speak about level statistics. If you consider this kind of Hamiltonian and you turn on both interactions, this one and this one, it's known numerically, and one of the invited lecturers, Marcus Rigel, put a lot of effort doing this stuff numerically. It's known very well that the spectrum of this Hamiltonian, after all, this is a large matrix. It's a matrix of the size 2 to the L by 2 to the L. You can diagonalize it. It's Hermitian. It will have a bunch of numbers. That's the spectrum. It's very well known that this spectrum obeys properties proposed by Wigner and outlined more carefully by Wigner, Dyson, and Mehta. It will satisfy those properties, but people don't really understand why, in a sense that we don't have a good derivation of this result. There is no classical or semi-classical limit here. We are dealing with the discrete spins. So we know experimentally or empirically that this is what is happening, and the notion of quantum chaos can be extended from semi-classical one-particle systems to this kind of systems, but there is not many rigorous results trying to derive these properties for the spin chains. Okay, right, so we will speak a bit about derivation, but there is really no good derivation. So I will start first from the historical formulation. So there are many works. So it's not a complete list of works, but these are 3 main works with people cite. One goes back to George Deutsch, then Mark Srednitsky, who certainly did a major contribution. And this formula is sometimes called Srednitsky ETH ansatz. And then also a paper in 2008 where Marcus Rigel and collaborators did numerical simulations confirming this behavior. So standard ETH formulation, standard formulation of ETH is a statement of an ansatz that matrix elements of certain observable have this form. Let me explain what this formula means. So let's consider a Hamiltonian like this. You can diagonalize it. That will give you eigenvalues. You can also find eigenvectors. Each eigenvector will be a vector of length 2 to the L. So this Hamiltonian is real, so this will be real valued vectors, but it could be complex. It doesn't really matter. So these states, Bryan-Ket states, are those vectors of length 2 to the L. Then you consider an operator A. In the case of a Hamiltonian like this, a typical operator people would consider could be a spin operator acting on a particular site. So for example, A could be spin X sitting at the site number 5, or sitting at the site number 1. My numerical plots, I have a few numerical plots to show you, will be for the operator sitting at the edge of the spin chain. So this is my A. And then I consider matrix elements of this operator. Sigma X is a 2 by 2 matrix, but I understand that I am acting by this matrix not only on one spin, but on L spins. So strictly speaking, this matrix has to be extended by identity matrices such that it becomes 2 to the L cross 2 to the L matrix. And then I'm calculating matrix elements of this matrix in a basis which is an eigenbasis of this Hamiltonian. Okay, that's what I'm mathematically doing. Now, naively, you would expect that what I will get is a mess. I have a nice matrix, Pauli matrix, 2 by 2, 0, 1, 1, 0. And then I multiply it by a large identity matrix. So I have a matrix 2 to the L, 2 to the L. Then I write it on some crazy basis, the basis which diagonalizes this Hamiltonian. What would I get? I will have a mess. There is no prediction. But a core observation is that, and that observation goes back to Deutsch and Srednitsky, essentially, mostly to these papers by Srednitsky, that matrix elements will have some natural form, and you can write a nice ansatz which invokes only a few functions. So the diagonal part mostly will be a smooth part. So mostly the diagonal matrix elements in this new basis will be pretty much the same. That's already a highly non-trivial observation. I'm telling you that you take a simple matrix, you bring it to a complicated basis, look at the diagonal matrix elements on the diagonal will be pretty much the same. And then off-diagonal matrix elements will be exponentially small, where S is the entropy. Entropy is the total density of states, and in my example, e to the S is essentially 2 to the L. Entropy is extensive, it's proportional to the volume, so e to the S is an exponentially large number. Then this ansatz includes a few functions. This function, the diagonal one and the off-diagonal one, all of these functions are smooth functions of its argument. Now, since I'm talking to a mathematical audience, I need to explain what it means, a smooth function to its argument, because this could be understood in the wrong way. I'm not talking about the standard calculus mathematical analysis definition of smoothness. I'm talking about stronger statement. This is a physical statement, not only a mathematical statement. Smoothness in this case means the following. You can consider a measure of smoothness such that the value of a derivative or a Lipschitz constant, for example, and then this maximal value of a Lipschitz constant or a derivative should remain finite as you increase the size of the system. I will have a plot with a picture where this will become a little bit more transparent, but the idea is the following. The eigenvalues of this matrix, there are 2 to the L of them, so they will be exponentially close to each other. This function, strictly speaking, is not defined for E, for an argument which is not an eigenvalue of this matrix. This function, by definition, is only defined in these exponentially close values. But I want to extend this function to be defined everywhere. So you have a grid of points, not periodic, but you have a dense grid of points which are exponentially close to each other. You define function of those exponentially close points. And of course, a smooth function can go through all possible values. Mathematically, it's possible. But if you do that, then the Lipschitz constant will be exponentially large. So that I will not call a smooth function. For me, a smooth function is a function with a Lipschitz constant, which is of order 1 in terms of the volume. I increase the volume, I increase the size of the spin chain, the Lipschitz constant of this function should not grow. That's a requirement. So it's very clear that if I formulated a requirement like that, to make it rigorous, I cannot formulate it in terms of one particular system. I need to have a class of systems, and I need to agree what I consider to be a volume or the size, and agree to grow that size and see how things change as the size grows. This is not completely different from what we heard at the previous talk, where we had h prime, or h, the Planck constant, which we would take to 0, or equivalently, we could take energy to be very, very large. That is an alternative language, which would effectively make things classical. So here, instead of having Planck constant, which is 1, there is no point of taking it to 0, because these are discrete things. We simply increase the size and see how things scale with the system size. Okay, so this is an ansatz. These things we cannot predict. We call them pseudo-random. Of course, they follow unambiguously from the form of this matrix, but we call them pseudo-random because there is no apparent structure to them. And perhaps we say, and we will speak about that a little bit later, perhaps we say there is no structure, physically meaningful structure in these numbers at all. So at first approximation, we say these are random numbers, and we choose them. That's our choice. That's sort of the gauge, maybe physics language to say the gauge, but that's our choice, to say that these are the numbers with 0 mean and variance 1, and whatever is, and we can always make them variance 1 because the overall amplitude can be absorbed into this smooth function. Now, at first glance, oops, okay, I survived. At first glance, you can think, and that's what is reflected in the literature, that the exponential factor here is something miraculous. People would say, you know what, ETH is a very strong prediction because it predicts that off-diagonal matrix elements are exponentially small. That's a very, very strong statement. In fact, this factor is kinematic. Kinematic means that it really is universal and is not rooted in the peculiarities of this Hamiltonian. And I will try to explain that in a second. But this factor follows automatically if you say the following magic words. If you say, I want most off-diagonal elements to be similar to each other, at least statistically, to be of the same order. You already said that about diagonal matrix elements. Well, here you have literally smooth function, but of course there is RNN, the fluctuations along the diagonal. So you already said that about the diagonal matrix elements. If you say the same about off-diagonal matrix elements, you say, I want statistically off-diagonal matrix elements to be approximately the same. This factor will pop up automatically. And therefore, it's not specific, neither for quantum chaotic, nothing like that. And if you consider integrable models, which are what is called interacting integrable models, where most off-diagonal matrix elements are similar to each other, you will also have this factor. Marcus might speak about that because his recent numerical results are related specifically to those integrable models. Okay, so this is what is called historical definition, which comes mostly from this paper, and that's the formula which is present in a myriad papers about ETH. That's perhaps not the best possible formulation, but it's a historic one, so I wanted to start with that. Okay, now an illustration. Now I want to convince you so that that formula is not just a mathematical way to present trivial things, but there is genuine observation behind ETH. So this slide serves the following purpose. It should convince you, it should convince you that there is genuine phenomenon behind ETH. I consider this Hamiltonian with 17 spins. 2 to 17 is how many? 130,000, something like that. Maybe I made a mistake, but I think 130 something. You can put it on a computer. You can calculate matrix elements for two cases. When both of them turn on, and this is non-integrable case, and when only one of them turn on, this is 0, and this is the integrable case. And you can plot diagonal matrix elements of this matrix A versus energy. Energy is not a continuous quantity here. You have 2 to the L, 130,000 different values of E, but since you have only that large of a distance and 130,000 different points, you perceive them as essentially continuous. And you see this obvious difference in the pattern. In the integrable case, you have, well, first of all, you have some structure, because this is not only integrable model, this is a free model. This is a model describing free particles, so everything is so simple. But more importantly, you have some cloud of points which doesn't shrink. Once you break integrability, and this is a generic case, you see this line shrink, and basically you have universality. If you consider two consecutive matrix elements along the diagonal, their value will be very close. In fact, it will be exponentially close. So this thickness is exponentially small. It's e to minus L, or 2 to minus L, 1 divided by 2 to the L. Okay? It's actually exponentially small, and you can check that numerically. So this is the most important slide when you want to ask the question where this is all coming from. This is coming from this observation. Okay, but then there are several different ways to think about this phenomenon and how to quantify it. Let's write again the ETH ansatz, but only for the diagonal matrix elements. You can have the diagonal matrix element where you have the smooth part. What is a smooth part again? A smooth part means that you have a smooth function here. Of course, it could be a little bit wiggly here, but if you increase the size by a few more slides, it will shrink even more. So this smooth function better be something like a line, maybe with some curvature, but it cannot be too wiggly. Mathematically, of course, you can have mathematically smooth function which goes through all of these points, but you understand that it will oscillate like crazy with the Lipschitz constant being exponentially large, because it has to go from minus 1/2 to 1/2 in the exponentially narrow step. So that I don't call smooth. So here, smooth function won't do, but here, smooth function will do. So you have a smooth function, plus you have an fluctuation around it. And there are two ways to quantify the difference between these pictures, or at least two ways. One way is to study variance statistically. And statistically, you will see that here, variance is exponentially small with volume, with the size. And here, you don't know, because this is a cloud of points, and it's absolutely not clear from this picture. Points are so dense on each other that you don't see any difference in color between this point and this point. They're all completely blue, completely blue. So from this point, from this picture, it's not clear what is the variance of these fluctuations, because it's not clear where you have more of this, more points and less points. Quite surprisingly, it so happens that the variance, even in this case, is also suppressed by the size of the system, but not exponentially, only polynomially. It means that there are way more points along this line. You have exactly the same line, like, well, I mean, exactly the same, not in a sense that it's in the same points, but it's the same style of line, which goes like this. And you have many more points along this line. You just cannot see them because you have points all over. And here you don't have points anywhere else. Here you have points somewhere here. And therefore, variance is only polynomially suppressed in the volume. It's suppressed like 1 over volume. So this is a statistical way to describe those fluctuations. There is perhaps a better way to study the largest possible fluctuation. Largest fluctuation here is of order 1. It will not shrink. If you consider 17 spins, 25 spins, 130 spins, you will always have fluctuations which are order 1 away from this main line. But if you consider this system, and people study that numerically, maximal deviation will be only exponential. So perhaps maximal deviation is the best language here. And historically, people looked at the maximal deviation as the hallmark of ETH. But a few years ago, people found systems which are in between being chaotic. Well, when I say chaotic, I mean generic. Really, I don't put any mathematical meaning in this word, besides that it's not integrable. People found systems between integrable and non-integrable, which are what is called quantum scarred systems, which have both exponentially small variance in terms of statistics, but also order 1 outliers, which are very, very rare. So there is a hybrid behavior. things are more complicated. You don't have a binary choice, you have something in between. Therefore, if you're especially mathematically inclined and you want things to be rigorous, you have to choose which definition to go with, and I believe this definition is sort of more robust because it doesn't care about exponentially few states which are very far away from this main line. Okay, so it's easier. Once we understand statistical properties, it might be possible to go back and study maximal deviations. But statistical properties is always easier. Okay, how is this? I do not know if there will be questions in the middle or maybe not. Perhaps not. Then let me try.
If people want to ask questions, we can circulate the microphone.
Okay. So there were no questions. I was just thinking that maybe if someone has a question, that would be a good point to stop because.
Just can you say what was V?
V is a volume. I'm sorry.
Okay.
V is a volume. Sorry, I did not explain that well. If we say that this function is smooth, meaning that the Lipschitz constant of order 1, I don't care whether 1 or polynomial in volume. It's more important that it is not exponential. From the physical considerations, you can say that this function should be smooth in terms of energy density, energy divided by volume. Then literally this function, the Taylor series of this function will become finite. All Taylor coefficients should become finite as volume goes to infinity. In statistical mechanics, the proper game is always to take volume to infinity. Mathematically, it could be challenging, but that's the right way to do it. And then if you consider function of this combination should remain finite in the thermodynamic limit, and this function should remain finite in thermodynamic limit. So that's the right way to write it, but historically people don't write V in the argument, and I followed these notations in the slide before. So historically people didn't write V in the argument, but the right way to do it is to include it because that's when you have proper thermodynamic limit. But these are the nuances which are less important. Let's speak about physical significance. Perhaps I convince you that there is a genuine observation behind the CTH. That indeed, if you have a computer and you diagonalize matrices, you see very different behavior. But let's try to understand what's the physical significance of this. The physical significance, why people paid so much attention to this, starting from the Nature paper by Marcus Rigel and collaborators 2008. That's because this simple mathematics can explain thermalization of isolated quantum systems. About 2 decades ago, 15 years ago, people learned how to build systems consisting of several quantum atoms, quantum meaning that they are coherent in the lab, and you can coherently evolve them in time. And they started studying how those things interact with each other and thermalize. But the word thermalization should be understood in a particular sense. These atoms are isolated from the environment. They can only exchange energy with each other. So what do we understand by thermalization? Conventional thermalization means that you start with some state and you end up in a Gibbs state. That's what standard textbooks tell you. That's what textbooks tell you what will happen if you have interaction with the environment. Here, the mathematical problem is different. You start with some state. Could be a pure state or a mixed state, it doesn't matter, but the evolution is unitary. You assume that your experiment is ideal and your system is completely isolated from the environment. Since your evolution is unitary, starting from some row which is different from this, you will not be able to evolve to this raw thermal. This arrow is not possible. If you have unitary evolution, this arrow is not possible. So what exactly do I mean by thermalization? Because the state of my system is never truly thermal. What is understood is thermalization at the level of expectation values. Let's start with some state. Let's say it will be a pure state. And let's evolve expectation value of an operator in time. So A is my operator, and I evolve it in time. It could be either a Schrödinger picture or Heisenberg picture. It doesn't matter. The formula is always the same. There are terms which are completely time independent, and there are also terms which are oscillating. In a nutshell, quantum mechanics is deceivingly simple because it's all about matrices, and time evolution is just phases. That's all. So at this level, quantum mechanics is the simplest theory ever, because time evolution in full generality for any operator, for any state, is given by this. In reality, these are complicated matrix elements A and M, and the initial state could be complicated. So this could be a rather complicated time dynamics in time. But let's do the following. Let's average over time. And let's average over time, meaning over the whole line of time. That's not a physical thing to do. In the real experiment, you can start with your system and involve it coherently, maybe for a few milliseconds. Maybe if you're lucky, you can involve for seconds if you want it to be coherent. If you forget about coherent time evolution and you allow your system to interact with the environment, you can evolve your system for days, months, years, maybe for billions of years. But the size, the age of the universe is 15 billion years, and it's very unlikely that you will be able to evolve your system for much longer than another 15 billion years, because everything will dissolve, it will be absorbed by the black hole, and so on and so forth. At the same time, if you consider a system which has macroscopic size, I don't know how many spins, but not that many, maybe 10,000 spins. To get what I want at the next slide, to get what I want the next step, to mathematically formalize what it means to integrate over the whole domain of time, you need to integrate your system over a period of time much larger than 15 billion years. Why? I didn't explain what I want to do. I want to integrate over the whole domain of time to completely cancel those terms. Those terms are oscillatory. They're oscillatory. And therefore, if I integrate them over the whole domain of time and average over all of the time, sooner or later, these terms will disappear. Mathematically, this is correct. But in practice, you have always exponentially close energy levels to each other. And therefore, you have to integrate over exponentially long times, which are not under our control, not only practically, but also conceptually. You cannot expect that you will have the same physical system for the exponential long time. All the predictions we do in physics, we do for times which are not exponential. So I'm doing a trick which is mathematically correct, but physically has no meaning. Because in physics, we cannot guarantee existence of our universe for exponential long times. I am completely pushing this aside. This is a logical inconsistency, very important one for physics, because if you propose something which is not physically possible, that may not have meaning. That is a very important physical principle. So I'm proposing something which might not have meaning in physics, but I'm integrating over the whole domain of time, and these terms disappear. Once they disappear, I have the constant here, and I'm saying this is the final value where my system will go to after it equilibrates. In reality, we do observe equilibration of a physical system which takes not exponential times, but very quick times. Hours, seconds, polynomial in system size if you have diffusion, but it's never exponential. So in practice, we always see, well, not always, but we very often see equilibration, but we never know if this equilibration is given by this term or this term is also included. We don't know. Nevertheless, if you try to do a numerical experiment with a spin chain, a miracle happens. And apparently, these terms indeed can be neglected. We do not know if this is because these are simple systems or something like that, but these terms can be neglected, and the equilibrated value which you observe after only polynomial time is indeed given by this diagonal term. This is a crucial step which can be, at this point, justified only empirically. Only empirically. I will postpone discussing this important transition because, in my view, this question belongs to the following category. The question is, can we really say something precise about thermalization dynamics? Can we really advocate that the equilibrated value which we observe after polynomial time is indeed given by this, and we can neglect this? So let me first assume that I can do that and see what is the mileage here. Excuse me, I'll make a very short break. Okay, so assuming that I can average over the whole time and only this term survives, and I equate this value with the equilibrated value, which is presumably my thermal value, I observe the following. If I postulated ETH, if I postulated that all diagonal matrix elements are very close to each other, then it really doesn't matter what my original state was, because all diagonal matrix elements are approximately the same, and therefore this sum can be taken individually, and this an can be put out of parentheses. The sum of Cn squares is the norm of my wave function, which is 1. And in the end of the story, I have full universality. So this is the most straightforward, important, and obvious consequence of Eigenstate Thermalization Hypothesis. It predicts that it doesn't really matter which state I started with. So far, I convinced myself that I can neglect those terms because I can integrate over the whole domain of time. It predicts full universality. The final value of my observable will be completely universal, independent on the original state.
But so
okay?
Originally, this AETH also depended on,
yes.
on the energy levels?
Yes. So first of all, this is a typo which comes from the previous talk. It should be ETH here. You can remove E, and that also has certain meaning, but let's not discuss that until the next slide. So this is ETH, and of course this ETH is a function. It depends on the energy, and it's a function here. It depends on the energy. It's a smooth function of energy. You see here it was more or less linearly growing with the energy. And the technical assumption here was that the state you consider, most of its matrix elements are located at certain energy shell. People can consider something what they call a thermal Schrödinger cat. That's a superposition of two states which have two different macroscopic energies. Because it's quantum mechanics, you can consider a superposition of any two states. Imagine that you have a perfectly thermal state at temperature T1. You have a perfectly thermal state at temperature T2. Consider a superposition of those two states. Since quantum mechanics is linear, your system will always be in a superposition of these two states, and nothing like thermalization to a common temperature will happen, ever, if you have unitary time evolution. So, of course, in reality, if you have interaction with the environment, you might expect thermalization to a common temperature. But if you have isolated system and you started in a superposition of states with two different temperatures, it will always be like that. A million years, an exponential number of years later on, it will always be a superposition of two states with two different temperatures. So we don't want to discuss that setup, because from some point of view it's trivial. It's just superposition of two states which are physically trivial. From another point of view, it's not practical, because in experiment we don't expect this to happen unless you prepare it like this. So we assume that the state here have certain mean energy, and that energy will enter AETH as an argument. Yes?
I have a question. You assume that there was no interaction between the two states. If there is an interaction, even if the whole system is closed, but if there is an interaction between the system with temperature T1 and the system with temperature T2, they can be thermalized.
I'm not sure I explain what I mean. I mean, you have state number 1, E minus beta 1 H over Z of beta 1, and you have the same state with a different, or thermal state with a different temperature. These are two density matrices. let's consider their superposition. This is a state, it is a quantum state, which has superposition of two temperatures, right? It will always be like that. This state is stationary. This matrix commutes with the Hamiltonian. It will always be like that. There is no interaction between those two states. Because quantum mechanics, at least within our current understanding, quantum mechanics is exactly linear, and therefore it will always be like that. Yes?
In addition to quantum ergodicity, sometimes people look at what is called quantum mixing, which has to do with off-diagonal elements. And so I just, like Steve Zeldich, thought about that. And I wonder if there is any connection, because there is, whether it's interesting to look at this. It is less often, I think, people mention it than quantum ergodicity, but it's still
I'm not sure I know what quantum mixing is.
But we can look it up. It's just
okay, I'm simply not sure what is the term, what this term refers to.
I mean, Steve wrote a couple of papers where he looked at these things. So.
Okay, well, I mean, let's discuss. I'm not sure, yeah. Okay, so first,
so I guess the Andrew level En are just eigenvalues of the matrix. Is it clear that the eigenvalues are
In, INN are diagonal matrices, diagonal matrix elements. These are not eigenvalues. These are diagonal matrix elements.
Is it clear that they are distinct if N and M are distinct? I mean, because I think you're using that.
Yeah, N go in my model, in my example, N go from 1 to 2 to the L. N is an index which counts all matrix elements. The basis, the Hilbert space is has size 2 to the L. In any representation you want, matrix A will have a size 2 to the L cross 2 to the L. So N and M go from 1 to 2 to the L.
No, I think you mentioned the possibility that En and Em are exponentially close, but I think he's saying that
so
they
could they be equal?
They could be equal.
If they're equal, then N equal M. Right. So the question is if you can have energy level degeneracy. Yes. It's a good question. I got carried away and I forgot to mention there are standard disclaimers in this business. People say we want system without level degeneracy. And that's usually easy to cook because you forbid certain discrete symmetries which usually accompany level degeneracy. So in this model, for example, there will be no level degeneracies.
But so generically, do we expect the En to be distinct?
Yes. Usually there is no level degeneracy, which means that all En are distinct.
Okay.
And unless you have discrete symmetries or other symmetries, you always will have non-degenerate spectrum.
Okay, thank you.
Okay, so why people call it quantum ergodicity? Let me explain. I'm losing my hope to cover everything I wanted to, so I will focus on important things. I think that's the right thing to do. What is quantum ergodicity? The terms seem to be exactly the same as in the previous lecture, but the meaning of this term is different here. What is ergodicity? Ergodicity is a property of a classical dynamical system to forget about the initial state. Of course, classical mechanics is deterministic. Strictly speaking, you always know where you started because you can evolve in time. But classical ergodicity means that it really doesn't matter where you started. If you wait long enough, you will cover the whole phase space allowed by your conservation laws, and you will cover it more or less homogeneously. No, I'm not an expert, so I'm not trying to formulate mathematically rigorous formulation, but I'm trying to allude to physical meaning of ergodicity. And then if you wait long enough and average over time, for example, then you really don't care where you started. That's what ergodicity is. You forget about where you started in a physically meaningful way. The same happens here. I just told you, I give you the derivation subject to certain disclaimers and so on, but the derivation is the following, the statement is the following. It doesn't really matter what your original state was. The expectation value of this observable is always asymptotically the same. It means you forgot where you started. That's ergodicity. It's quantum because I'm considering quantum system in a quantum state. So the meaning of quantum ergodicity in this context is that the expectation value of your observable at late times is completely not sensitive to the peculiarities of the initial state. So in that sense, at the physical meaning of this, it's a quantum analog of classical ergodicity. There is also another mathematical, very clear mathematical result related to the ETH ansatz. You can try to calculate how big will be fluctuations around the asymptotic value. So we all agree that if you allow me to integrate average over the whole domain of time, no matter whether physically this is meaningful or not, you will end up with some constant. But it's clear that if you look at the value of your observable, it will fluctuate around that mean. So we want to know how big those fluctuations. It's very easy to show that if you assume absence of degeneracy, and that's a standard assumption, it's actually have to be a little bit stronger. You not only assume that energy levels are not degenerate, you also assume that what is called gaps. Gaps are pairs of En minus Em. Gaps are not degenerate means that En, you probably cannot see. En minus Em is equal to Ek minus El means that N equal K and M equal L, unless N equal, or N equal M and K equal L, okay? Most systems without symmetries, they satisfy that. There's no proof to the extent I know, but it's an empirical fact which you can check on a computer. So with this technical assumption, it's very easy to show that the fluctuations around the asymptotic value, mean value, will be bounded by the largest off-diagonal matrix element. And I was promising you that off-diagonal matrix elements kinematically exponentially small, so far they're all similar to each other. So if you assume ETH, if you assume statistical properties, then this is exponentially small. So not only we predict that asymptotic value is universal, we also predict that you will not fluctuate much around this asymptotic value. These are two physically very important, very strong predictions which you got pretty much out of nowhere, out of very minimalistic assumptions. So that's why people really like ETH. And then this is the slide about different notions of quantum ergodicity. I want to draw a distinction and similarity. In the previous lecture, quantum ergodicity referred to the property of the wave function of being equally spread. If you have a particle hopping on a graph, like for example in this case, you have a particle hopping on the graph, so the I is the basis of the Hilbert space associated with the vertex number I of a graph. But this is a single quantized picture. And if you assume that your particle is more or less spread, the eigenstate of your Hamiltonian describes a particle which is homogeneously spread across the system, then it's also ergodicity, which is physically very similar to the ergodicity I just described before. And in fact, I do not know if there are rigorous mathematical results, but from the physical point of view, if you consider single quantized one-particle systems which are quantum ergodic in the standard way, how it was presented to us in the previous lecture, and you consider an observable which is spatially located. For example, it's an observable which tells you what's the probability to find the particle in a particular point in space, then both definitions of ergodicity will be the same, at least physically will be the same. But if you consider many-body systems like this, then to extend this definition of ergodicity is very difficult. Because now my I state is a particular state with up and down spins. Now I have I which goes from 1 to 2 to the L, and state I is a state like this. And there is no physical reason to expect that an eigenstate of my Hamiltonian will be more or less equally spread in this basis. There are statements which tell you how much it will spread, and people study that, and they use this quantity which called inverse participating ratio, and so on and so forth. But even if your system is physically ergodic in a physically meaningful sense, you don't expect all basis states to participate equally. And therefore, for many body systems, two notions of ergodicity, I don't think they're the same. And I don't think they have to be the same. The definition I stick with, it's more physical in a sense that it alludes to independence on the initial conditions. For the single particle context, I think both definitions are pretty much the same. But for many body contexts, I think these are two different properties. And I think this property is simply not satisfied for the many body systems. I do not know when exactly I started.
31. I mean, as far as I'm concerned, if you go over time of 5 minutes, it's okay.
Minutes. Okay. Okay.
I don't know if there are strict rules for. Good.
Good. I'll try not to go too much over time, because it seems like I'm covering the most important things. So far, I only predicted that my expectation value will be universal no matter where I started. But it automatically follows, you don't have to postulate it as a separate thing. It automatically follows that this value will be thermal expectation value. There is a difference between equilibration and thermalization. You can start with a system. In a non-equilibrium state, it will evolve somewhere and become steady. But you don't know if that steady value is really a thermal value or not. If you have equilibration, it might be to a value different from the thermal value. That's a logical possibility. Thermalization is a stronger statement that you not only evolve to some steady state, but this state is thermal. So if you postulate ETH, if you say that all diagonal matrix elements are pretty much the same, you don't have to distinguish between equilibration and thermalization. Whatever value you equilibrate it to automatically will be thermal value. And that simply follows from the definition of a thermal value. You need to average your observable in an ensemble. There are two standard ensembles, the microcanonical and canonical. And then essentially what ETH gives you, it gives you a new notion, what is called the eigenstate ensemble. It's not an ensemble because it consists of one particular state, which is an eigenstate, but apparently it's enough. And it's a very simple calculation to show that the values in all of these ensembles are very close to each other with the difference suppressed as 1 over volume. All right, so that was sort of an overview of previous results. I gave you the observation and try to convince you that there is some interesting phenomenon. I also try to give you some physical significance. But I did not try to give you precise definition which will zoom on important properties, and I did not try to give you the derivation. I will not try to give you derivation at all because there is no time, but I will try to give you a little bit more precise definition that refers to my work. And the general attempt was to understand a little bit better what ETH is all about. One basic question to ask, which operators satisfy ETH? That's the first question. I considered one spin operator at site 1. What if I consider a spin operator at site 2? What if I consider a product of those operators? Will they still satisfy ETH? With some numerics and some general arguments, we argued that if you can split your system into two parts, and one part is significantly smaller than the other, then it really doesn't matter which operator you consider so far it acts on this smaller system. And in fact, you can formulate ETH without a reference to an operator at all. You can formulate it at the level of reduced density matrices. So you consider the eigenstate, and you reduce this eigenstate to a subsystem, and you claim that the resulting reduced density matrix have some universal form, Basically, you have exponentially small oscillations, fluctuations around some universal form, and already at the level of density matrix, you can formulate the ETH. This formulation is known in the literature, and that's how we named our paper, which I think was the best marketing move. We called it the subsystem ETH. So we formulate everything in terms of the subsystem without any reference to the local operator. And then thermalization means that the whole state of the system never becomes Gibbs state, it never becomes thermal state. But if you consider reduced density matrix, then as time progresses, it really becomes thermal state of a subsystem. So at the level of reduced density matrix, you can indeed observe emergence of a Gibbs state.
And so beta appears as some kind of Lagrange multiplier?
Excuse me?
The temperature beta?
Yes.
Is it,
you need to match beta to energy through the standard relation that this beta is chosen such that the average energy at the temperature beta is E, which is used to define this universal matrix. It's a Lagrange, yes. The standard relation through a Lagrange multiplier.
And the state that you have above is the entanglement entropy of A?
Excuse me?
Above in the formula you have SA minus S22.
Yes, yes. These are not entanglement entropies. These are thermodynamic entropies, but perhaps you can make them entanglement as well. But E to the S is a density of states. So in that sense, it's not entanglement entropy, it's thermodynamic entropy. What is SA? It's a density of states of a subsystem A. It's not well defined because it might depend on the boundary conditions, but it's quite often in statistical mechanics, it's all defined in the limit when you have large volumes and you forget about boundary terms. So, and that's why we put O here. You can, once you start making mathematically precise statements, you can clarify this O is. By the way, the factor SA here is our conjecture, which we somewhat check numerically, and we have some analytic argument, but that's really a conjecture, meaning I cannot bet my life on this result. So this factor here without 2 is what we propose. It certainly will be interesting to understand if it is like that, or it just we were deceived by those examples we considered. But yeah.
Can I again ask?
Yeah, yeah.
Is it like philosophically the same thing as page theorem?
Could you please say again?
Of page theorem?
Yes. Good. So I will reformulate your question a little bit. The question is our result helpful to calculate entanglement entropy of energy eigenstates? And in fact, yes. You can look at this paper in the appendix, and we basically give you the prescription to calculate entanglement energy of the eigenstates. And this prescription was followed in the literature, and there is a paper by Grover and Lin, which I can give you the references, and then also then later by Mark Skridnitsky and Murphy, and then on a high energy side by Shidon and other people, and they work out some important, and then Marcus Rigel worked on that recently. They work out some important corrections to the page curve in the middle of the page curve. Not the page curve for the random state, but the page curve for the eigenstate of a spin system. And basically, the starting point was our paper where we say that once you have ETH of this form, there is a semiclassical formula for the entanglement entropy. What they work out is sort of correction to that, which is not covered by semiclassics. This is a correction, but at least semiclassically, the universal formula is just following from here. Thank you for this question, otherwise I will not mention it. I think it's time for me to wrap up. And I will not go through the proof. I'll just say that there is no derivation of ETH. All the statements they made are empirical statements which people did with a computer and check with a computer. Nothing is easy to prove. It's not even clear where this is coming from. But there is a version of ETH called weak ETH, which says that in the worst case scenario, these fluctuations are polynomially suppressed, even in the worst case scenario. The proof is elementary. I have it on 2 slides. Nothing, bunch of trivial inequalities. And it's very nice, very simple, but there is a huge gap between polynomial suppression and exponential suppression. Exponential suppression is not universal. It only works in a generic system, in a chaotic one. This result is elementary, but universal. So it's very clear that if you want to improve from polynomial precision to exponential precision, you need to do something completely different. So weak ETH is a very interesting result. It's completely universal, but it doesn't really give you the essence of ETH. It really tells you that these quantities are exponentially small. Now, somehow I felt that I will not go very far with my presentation. One more minute. I want to show you the plot of off-diagonal matrix elements. And the punchline here is that if you have non-integrable case, you can discuss them statistically. And the integrable case, there is some structure which do not allow you to discuss them statistically. You see this like a fountain or something like that. Obviously precludes statistical discussion. And I made a slide. My talk presumably should go on for another 10 or 15 slides covering all kind of different things, dynamics and quantum field theory. Nothing of that will happen today, but I have a slide in the middle which will serve as the end because it basically should end this part. And let me try to reiterate. So I wanted to convince you that there is some phenomenon, an observation. And I wanted to tell you that there is some precise formulation. And we were trying to give this precise formulation at the level of subsystem ETH. But I really think that this is only part of the story. I really think that the right way to think about Eigenstate Thermalization Hypothesis is not a particular specific answers for the matrix elements. I think the statement, the physical statement and mathematical statement should be slightly different. The statement should be like that. I'm not sure if it is on this slide, but maybe here. The statement of ETH is that one should really think about matrix elements of a generic non-integrable system in the statistical terms. The statement of ETH is that you say that individual matrix elements don't have their own individuality. You can consider an ensemble of them. Very similarly, like Wigner said, that individual energy levels cannot be described in full detail, but you consider an ensemble of them and you study their statistical properties, and then it becomes mathematically beautiful, tractable story with a clear answer. I believe this is the true message of ETH, that one should study statistical properties of off-diagonal and diagonal matrix elements and try to find a random matrix model which describes them. And Jorge and his collaborators in the room, they recently had a paper about this. And I personally believe this is the right direction in a sense that the correct formulation of ETH, I believe, should be along these lines. We should have a statistical description of those matrix elements, maybe in terms of random matrix model, something like that. After I said all of that, there are a lot of questions to explore, even in the single particle settings. You forget about all of this. You go to the previous lecture, to the single particle hopping on a graph or a single particle exploring a Riemann manifold, and you ask if you can really describe off-diagonal matrix elements and matrix elements of some observables, and if you can really see some universality. I will not speak much about this because this is an unexplored thing, but I think that this will lead to some interesting and well-formulated mathematical problems. With this, I will thank you and stop here.